Hi, this is Steve Denenberg. In this next series of videos, we are going to talk about the physics of springs and simple harmonic motion. So what is a spring? Here we have an example of a spring. There's a wall to which the spring is attached, and this spring is attached to a mass at the end of the spring, and the mass is sliding on a friction-free surface. A spring is a mechanism such that the force from the spring trying to move an attached mass is proportional to the distance from its equilibrium position. So what does that mean? If the mass is not moving, then the spring is in its equilibrium position. Right here, it's not stretched and it's not compressed. It's just sitting. If you move the mass, if you pull the mass, you're stretching the spring. And the amount that you have moved the mass is proportional to the force that the spring will put on the mass trying to go back to the equilibrium position. Similarly, if you compress the spring, if you push the mass in and make the spring tighter, the spring is going to provide a force that is proportional to the amount that you moved the mass that is trying to push things back to the equilibrium position. So if you move the mass a distance x sub naught, and you always have to measure from the same part of the mass, so you've moved the mass this far, force that tries to push the mass back to the equilibrium position equals the amount that you've moved it times a constant. That's what proportional to means. It means it's times a constant. Well, it's times a constant, so this sounds like a good place to draw a chart. So let's say we have x here. Let's say we have the distance that the spring has been moved from its equilibrium position, and this is the magnitude of the restoring force. As the distance from equilibrium position goes up, the force goes up proportionately, because we say F equals kx. Now that looks very much like the equation for a line. Y equals mx plus b, right? We know that. So this is the equation of a line, and this is the equation of a line if F, the force, is on the y-axis and x is on the horizontal axis. And the slope of this line is m, so the slope of our force distance line is k. And that's the force distance chart for a spring. The larger the distance away from the equilibrium position, the greater the force that is trying to restore the spring to its equilibrium position. Actually, what we say is that F equals negative k times x. And why is that? Here's our mass in its equilibrium position. If you stretch the spring, pulling the mass out from its equilibrium to the right, this is the positive x-axis, the restoring force will be pulling the mass this way, back toward equilibrium. So the force is going to be opposite to the displacement. If the x displacement is positive, the force is negative along the x-axis, so we say F equals negative k times x. And similarly, if here is equilibrium position and the displacement is negative along the x-axis, the force trying to restore the mass is positive along the x-axis. So F equals negative k times x. Next, let's investigate the units of this spring constant k. We say F equals negative k times x. Now F equals ma, mass times acceleration, which is how I always remember the units. Mass times acceleration is kilograms times acceleration, which is meters per second squared. And that equals negative k times x, but x is just in meters. So the spring constant has to have some units of its own. And let's do it like this. We say negative kx equals F. Negative k equals F over x, and k equals negative F over x. And what are the units of this? This is newtons. Force is newtons. This is newtons per meter. Well, that makes sense. Newtons per meter sounds right for a spring, which gives a force proportional to the distance it's stretched. You pull the mass out 1 meter, the restoring force is going to be k newtons per meter times 1 meter, which equals k newtons. Or you pull it out 8 meters. The restoring force is going to be k newtons per meter times 8 meters, or 8k newtons. Your force is going to be in newtons. Now, how does the mass move when you pull it out and let go? Well, you know what's going to happen. It's going to oscillate back and forth. It's going to be back and forth and back and forth. And that kind of seems like a trig function, like a cosine function. And in fact, what we will learn is the position of the mass along the x-axis at a certain time is going to be very close to the cosine of the time. And I'll give you a little feel for that here. If here is a cosine curve, and you are looking at it from here, seeing it edge on, while a bead is following the cosine curve, you're going to see that bead going up and down and back and forth as it travels along the curve. And that's going to look very much like the undulations of a cosine or sine trig function. Or even better, let's look at something called a Scotch yoke. This is what we call a Scotch yoke. You can see the post going around in a circle, and the guide is going back and forth along the x-axis, back and forth, exactly as you would expect the block to move on the spring. And this is what we call simple harmonic motion. Now, since the guide is directed along the x-axis, it is showing us the cosine of the angle that the post is making along the unit circle. So here we have a cosine of 1, and here we have a cosine of -1, and here we have a cosine of 0 when the post is up at the top of the circle, where the angle is pi over 2. Get it? Now, before we go any farther, we have to pause to make sure we are absolutely solid on 3 concepts of repetitive motion like this: the period, the frequency, and the angular speed. Here we have a cosine curve. Y equals cosine of x. Actually, this curve is y equals cosine of something x. And we'll get to that later in the video. But so the cosine function goes up and down and up and down. The period of this motion t is the distance between 2 points that are 1 full cycle apart. From the apex of the curve to the apex of the adjacent curve. So this is the period of the cosine curve. If the y-axis is time, then this distance along the y-axis is in time, and the period, how long it takes for 1 full cycle, 1 vibration, 1 full rotation. So if the x-axis is in seconds, then t is in seconds. So if the distance between here to here is 10 seconds, the period is 10 seconds. It answers the question, how long? How long between full cycles? And note the units, seconds. It's a measurement of time. Frequency is 1 over the period. So if you have a period of 0.5 seconds for one full vibration, one full cycle, then the frequency is 1 over t, which is 1 over 0.5, which is 2. And the units are seconds to the minus 1 per second. That tells you how fast something is happening. How many meters per second? How many vibrations per second? That tells you how fast something is moving. The period tells you how long it takes for a vibration to happen. So if the period, if the time is 0.1 seconds, the frequency equals 10 per second. On a piano, the A key that is above middle C vibrates at a frequency of 440 hertz. 440 full cycles per second. So the period of the vibration is 1 over the frequency, which is 1/440th seconds. I hope this sounds elementary, but sometimes jumping between period and frequency and angular speed can be confusing. So the period tells us how long it takes for something to happen. The frequency tells us how fast it's happening. What does angular velocity have to do with either of those? Where is the angle that is moving? If we take our cosine function again, let's look at where the angles are. If this is strictly y equals cosine of x. I know the labels are not accurate on this diagram. So here the angle is 0. Where the cosine drops to 0, the angle is pi over 2. Where the cosine is -1, that's an angle of pi. Where the cosine hits 0 again, that's 3 pi over 2. And where the cosine is back to where we started, one complete cycle, the angle is 2 pi. So now let's picture the entire unit circle. And let's look at cosine of x. We go from an angle of 0 around the circle to an angle of 2 pi from peak to peak of the cosine curve in the time period t. So one cycle of the cosine curve is all the way around the circle if we're looking at the angles. And during that one cycle, this fictional hypotenuse of the unit circle, as it's traveling around, it travels 2 pi radians. So if we go 2 pi radians in time t seconds, the period of one full vibration, then what do we have? Just like distance equals velocity times time, when we're looking at linear motion, angular distance equals angular velocity times time. Angular distance is in radians, angular velocity is in radians per second, and time is in seconds. So the units work out. So in one complete rotation, the angular distance is 2 pi, the angular velocity is omega, and the time is t, the period. So let's keep going. 2 pi equals omega times t. Omega equals 2 pi over t, which equals 2 pi over the reciprocal of the frequency, which equals 2 pi times the frequency. So we have omega, the angular velocity, equals 2 pi times the frequency, which makes sense to us because f is complete cycles per second, and one cycle is 2 pi radians. So as f does 1, omega is going to do 2 pi. 2 pi times as much as f. And note again that they have the same units, seconds to the minus 1. And now why don't we find these formulas on the very sheet that they give you at the beginning of every AP Physics 1 test to remind you of these formulas. Here we have the period is the reciprocal of the frequency, and the period is 2 pi over omega. So we can work that out by a cross multiplication. Omega equals 2 pi f. Okay, got that figured out. So our next question is, how fast does this spring oscillate back and forth? And what did we say how fast is? What is its frequency? How fast does it oscillate? Well, let's just think about it for a second from our knowledge of the world. You can imagine that the back and forth oscillation, the frequency of oscillation, depends on the strength of the spring, which we represent in our equation by K, the spring constant. How many newtons of force does the spring put on an attached mass per meter or centimeter or millimeter of displacement from the equilibrium position? Think of the thick, stiff, strong spring that supports the frame of a car. A very large spring constant in newtons per meter. You would think that that would be a very rapid vibration, and indeed it is. You hit that spring with a hammer, and it'll vibrate so fast that it'll put out an audible tone back to you. Whereas, if you had a really weak, loosey-goosey spring with a very small K in newtons per meter, you pull it a lot, and it hardly has any restoring force, you can imagine that that would have very slow, languid oscillations. Remember that the restoring force is proportional to the displacement times the spring constant. If the spring constant is very small, then the restoring force is very small. And since force equals ma, if the restoring force is very small, then the acceleration is going to be very small. Okay, so we decided that the frequency depends on the strength of the spring. You can imagine that it depends on the mass that's at the end of the spring. Here you have a mass at the end of a spring, and it's going back and forth. But then imagine the same spring and a mass that is much, much bigger. You have the same spring, the same K, the same force per distance stretched or compressed. But once again, since that same force is now working on a much bigger mass, the acceleration is going to be much smaller, and the mass is going to move slower back and forth. And indeed, that is exactly what we find. The frequency of oscillation of the mass on the spring, how fast it goes back and forth, the number of full cycles per second equals 1 over 2 pi times the square root of K over m. That's the square root of the spring constant divided by the mass that the spring is attached to. Just like we thought, a bigger spring constant, a stronger, stiffer spring, will result in a higher frequency of back and forth oscillation. And a greater mass, if the denominator gets big, then this gets small, and the frequency gets small. a greater mass results in a lower frequency of oscillation. And let's be sure we know what we're talking about when we talk about frequency of oscillation. We're talking about the mass going from one position in its oscillation, let's say the most extended position, all the way back to the most compressed, and then all the way back to the most extended again. That's one cycle. 10 of those in a second, and you have a frequency of 10. Now, since the period equals 1 over the frequency, we can say that the period of oscillation equals 2 pi times the square root of m over k. If the mass is big, the period is going to be big. It takes a long time to go back and forth. And if the spring constant is big and the spring is strong, then the period is going to be small. And one more thing, let's check the units. The period is in seconds, equals 2 pi is unit free, times the square root of the mass, which is kilograms, and the spring constant is newtons per meter. A newton is force, which is MA, so that's kilograms meters per second squared divided by meters. So these will cancel out. In the denominator, this cancels out with this. And so now we're left with 1 in the numerator and 1 over seconds squared in the denominator, which equals seconds squared. So we have seconds equals the square root of seconds squared, and the units work out. Oh, and let's go find that on the formula sheet for the AP exam, shall we? Here's our formula sheet, and there it is. The period of oscillation for a spring is 2 pi times the square root of mass over spring constant. All right, let's take another look at that. We had the frequency of oscillation equals 1 over 2 pi times the square root of k over m. And now you're saying, where on earth did you come up with that? We haven't done any equation manipulation to come anywhere close to something as bizarre looking as this, even though it makes sense. Well, the answer is, we said that the restoring force equals negative k times x. So we're going to say the mass times the acceleration equals negative k times x. Here we have mass, and here we have k, just like in the equation for the frequency. This right here is what we call a differential equation. And solving it is probably a second or third semester calculus class problem. But the result of solving this differential equation is that the x position for a certain time is going to be like the cosine function with these parameters for the frequency of oscillation of the cosine function. We've already seen a differential equation, but you probably didn't recognize it as such. If you have a ball dropping off a cliff under a constant force of mg, we have F equals mg. And that is also a differential equation. And the solution of that differential equation says that the position y of the ball equals the initial velocity of the ball times time plus 1/2 the acceleration times t squared. And we studied that equation quite extensively in the first videos of this channel, and this equation falls out of the solution of this differential equation. And with that, we'll conclude this video, but not our discussion of the physics of springs. First up in the next video, amplitude. See you there.